the invisible black hole that is headed straight for Earth. The background star brightened for 40 minutes, then slid back to normal as if nothing had happened. No flare, no explosion, no object in the frame. Just gravity bending light like a finger pressed into water. Out beyond Pluto, a silent ripple tugged at the Oort Cloud, tiny, unannounced, and gone. If something heavy can cross our backyard without a glow, warning time evaporates. Rogue stellar mass black holes, the dark corpses of dead stars, drift fast through the Milky Way. One nearby signature might already be on a predictable track. If we're wrong about the warning time, everything we care about moves onto a shorter clock. To see how we could miss a monster, go back to the first time we caught one without seeing it. The first ghost we actually saw. They called it a microlensing event, just a bump in a light curve from a star in the crowded bulge of the Milky Way. It didn't look like much, but the shape was odd. The rise and fall were stretched in time, and the baseline didn't misbehave the way a variable star would. On the ground, Ogle flagged it. In orbit, Hubble took aim and waited for the tiniest sideways nudge, an astrometric shift no bigger than a hair's breadth at the moon's distance. If the nudge was real, it meant there are things crossing our sky that only gravity can reveal, things that won't warn us until they're already here. Here's why that mattered. A microlens brightens a background star when a massive object drifts in front of it, bending the star's light. Most lenses are normal stars. They add their own photons to the scene. This one didn't. No extra light, no color change, just gravity. And Hubble, with months of patience, measured the star's apparent position inch sideways and slide back, parallax caused by the lens's mass tugging the light path as Earth orbited the Sun. Meanwhile, on Slack threads and midnight calls, the team traded bets. Some thought it'd land in neutron star territory, 2 or 3 solar masses. Others argued the timescale was too long for anything but a heavier lens. Week by week, the astrometric curve settled, the error bars tightened, and the fit snapped into place. Mass around 7 suns. No sign of a companion. No light from the lens itself down to the instrument limit. If it were a star, it should have shown up. It didn't. This was the moment everything changed. Not because black holes were new. We've had them in binaries, in X-ray fireworks whispering through LIGO's merger chirps. But this was free-floating. No donor star. No accretion glow. Just an object, dark and alone, passing in front of a distant background star and leaving a measurable gravity signature. The first confirmed isolated stellar mass black hole. And if one can walk past us unnoticed, the question stops being if and becomes when. It reset a quiet assumption. We told ourselves most dangerous things in the galaxy announced their presence. This one didn't. It drifted through our field, left fingerprints on a distant star, and moved on. If that's real, and the data said it was, then space between stars isn't empty. It's populated with dark lenses powerful enough to change orbits, inject comets, and never light up. While that was happening in one patch of sky, something else was brewing in the data oceans. Gaia's third data release, built from years of watching bright stars wobble with micro-arcsecond precision, started to surface candidates. Compact object lenses hinted at by astrometric shifts that didn't match binaries. Not proofs, not yet, but signals that multiplied as the catalog grew. The pattern was simple. More hints of heavy, dark things deflecting starlight without shining. Back in the lab, the human moments were small but telling. Someone scribbled BH next to the event ID on a whiteboard and refused to erase it for months. Coffee went cold during late-night fits when the parallax solution stubbornly preferred the higher mass. There was a micro-story of a grad student who promised not to get attached, then quietly told their advisor they were 90% sure. But I want the last 10 to be boring. It wasn't boring. There was one problem. Lensing is a drive-by. It gives you mass and velocity projected on the sky, sometimes a distance estimate but no persistent beacon. Once the alignment is over, the lens fades back into invisibility. You can't tag it with a radio transmitter. You can't point a telescope and see a surface. The measurement is a one-time dance between 3 bodies, the background star, the lens, and Earth's orbit. If you miss the beat, it's gone. That's why the impact was less a single discovery and more a shift in confidence. A confirmed free-floating black hole gave cover to whole catalogs of dark lens candidates. Suddenly, the invisible had a headcount problem. The implications stretched from astrophysics to risk. If a 7 solar mass ghost can cross a galactic field, and the only trace is a subtle brightening somewhere towards Sagittarius, what else passes closer, where star fields are sparse and alignments rare? What nobody knew at the time was how quickly the detection toolbox would change. Roman's design promised space-based microlensing parallax across wide fields. Rubin would sweep the sky nightly, catching more long timescale events. Gaia would keep tightening its astrometric net. But in 2022, with Hubble's measurement, the field crossed a line. We weren't guessing anymore. A dark lens had been weighed. From that point on, every quiet patch of sky felt less empty, and every non-detection meant our clock was still running. To understand why, we need to go back to the basics of motion. Every dark lens has a path and a speed. Natal kicks from supernovae can fling remnants into halo orbits, sending them arcing through the disk like commuters crossing lanes. Some wander near the sun's neighborhood, quiet and fast. We'd assumed nearby meant noticeable. The first ghost showed how wrong that comfort was. This decision by nature to hide mass without light would haunt planning. Detection became a choreography problem. You need the sky, the right cadence, the right alignment, and the patience to wait for a curve that takes months to unfold. And when it does, you get a handful of numbers: mass, proper motion, a distance box. Enough to say what it is, not enough to say where it's going next with certainty. Still, that first confirmation cracked something open. It turned an abstract threat into a measured presence. An object with no photons walked through our data and left a footprint. And once you see one set of tracks, you stop telling yourself the path is empty. How many rogues are out there? To get real about risk, we have to count the dark. Not guesses, orders of magnitude with reasons behind them. Start with stellar evolution. For every massive star that ever lived in the Milky Way, there's a chance it ended as a black hole. Roll the galaxy's star formation history forward, apply initial mass functions, and you land on a sobering range. Somewhere between 100 million and a billion stellar mass black holes drifting through the Milky Way. That's the background you never see, the fossil record of dead suns. But models only go so far, so we cross-check with a very different instrument. The universe itself ringing like a bell. LIGO and Virgo hear black holes collide. Those merge rates, when you fold in the volume of space they survey and how often they catch an event, imply a large hidden population. The mergers are the loud moments. Between them, most black holes are quiet. If coalescences happen this often, there have to be far more black holes not merging right now, living out long, dark lives. Now layer in dynamics. Black holes don't just sit where they're born. Some get natal kicks, momentum shoved into them by asymmetric supernova explosions. Others form by direct collapse with little kick but inherit the motion of their parent stars. Cluster dynamics can eject remnants, slinging them into the halo on plunging orbits. The result is a mixed population, some gliding with the disk, some cutting steep paths through it like hailstones through a roof. Speeds matter. In the disk, typical velocities are tens of kilometers per second. Halo crossers can run into the hundreds. That's the difference between a slow tide and a stone skipping across a pond. Faster lenses spend less time near any one place, give shorter windows for accretion, and make alignments briefer. But they sweep more volume. Over millions of years, they pass through neighborhoods we care about. So what's the density near us? Here, S where uncertainty bites. Take the conservative end. Say 100 million black holes in a Milky Way with a stellar disk roughly 100,000 light-years across and a thickness of about 1,000 light-years. Smear that population realistically, more in the inner regions, fewer outside, and you still get a local number on the order of a few tens per million cubic parsecs. Push the upper population bound, shift some into the halo, and the local disk number changes, but not to zero. For back-of-the-envelope intuition, That can translate to roughly one stellar mass black hole within a few dozen parsecs at any time, with wide error bars. The bands matter. If the true count leans high, the encounter math shifts. If natal kicks are stronger than we think, more black holes spend their lives in halo orbits, making fewer slow passes but more high-speed grazes. If more form by direct collapse without kicks, they track the disk's kinematics and share the sun's general motion, raising the chance of longer, slower encounters that tug more gently but for longer. Meanwhile, another clue sits in how often we see microlensing events with unusually long timescales. Surveys like Ogle and MOA pick up thousands of lenses. Most are stars. A small tail stretches into longer events that could be heavier objects. When you fold in astrometric shifts from Hubble or Gaia for a subset, the mass distribution hints at a tail of dark lenses. It's not a clean census. Selection effects are everywhere, but the tail exists. What nobody knew when the first free-floating black hole was weighed was how these lines of evidence would start to converge. Gaia's extended mission pushes its astrometry into finer territory. Roman will stare at dense fields long enough to nail parallax on lensing events, separating stars from compact objects. Rubin's cadence will spray the sky with time-domain data, expanding the pool of strange light curves. Each new dataset will drag the error bars inward. There's another layer people don't like to talk about: survivorship bias in binaries. We find black holes easily when they feed from a companion. Those are the loud few. The quiet many never had a companion or lost it long ago. If you only count talkers, you miss the crowd. Population synthesis models try to correct for that, but they depend on assumptions about metallicity, star formation bursts, and kick distributions. Small tweaks swing totals by factors. So where does this leave the risk ledger? With humility. The Milky Way likely hosts hundreds of millions of stellar mass black holes. A fraction share the sun's general orbital radius. A smaller fraction pass within a few parsecs over million-year timescales. Shrink the distance to a light year, and the probability per million years drops sharply, but it doesn't vanish. The neighborhood isn't packed, but it's not empty. Here's the emotional core. The numbers aren't scary because they promise doom. They're scary because they erase false comfort. You don't need one in a million to be pointed at us. You just need one in hundreds of millions moving through the right patch of sky at the wrong time. And because most are dark, the only advance notice we get comes from gravity's fine print. If we miss that fine print, we trade certainty for luck, and luck is not a plan. Knowing the count is step one. The fear, the hope, and the plan live in speed and trajectory. Where they go next writes our odds. The ways they hide, why we don't see them. Here's the part that messes with your gut. These things don't shine. A black hole gives you no photons, no surface, no silhouette unless it crosses something bright or eats something messy. Gravity is the only tell. That's why warning time collapses. You can stare straight at one and never know, unless a star behind it flinches. So we lean on the tricks gravity gives us. Microlensing is the loudest of the quiet methods. When a dark lens drifts in front of a distant star, the star brightens along a smooth curve and then fades. If the lens is heavy enough and the alignment is good, the event stretches over weeks to months. Pair that with astrometric lensing, the tiny sideways shift in the star's apparent position, and you can weigh the lens. But there's a catch. These alignments are rare. The lens, source, and Earth need just the right geometry. Miss the season, you miss the show. Accretion would make life easier. When a black hole runs into gas, it heats the infalling material and you get X-rays or radio. That's how we find black holes in binaries. Out in the field, though, fuel is thin. The local interstellar medium is hot and sparse, atoms per cubic centimeter. Bondi accretion from that soup is a trickle. You might get a faint radio whisper, maybe an X-ray transient if it cruises through a denser cloud. Most of the time, nothing. There's a more subtle signature, a dynamical wake. A massive object plowing through gas drags some of it along, leaving a denser trail. In principle, that wake emits. In practice, it's faint and smeared out, and the Milky Way is busy. You're trying to notice a ripple in a choppy sea. Even big radio arrays struggle to separate a black hole's wake from everything else glowing and hissing in the plane. Okay, what about the surveys? Gaia has phenomenal astrometric precision, but it's tuned for stars bright enough to measure cleanly, and it revisits on a schedule that wasn't built for microlensing alone. It still catches astrometric shifts, but only for certain magnitudes and timescales. Rubin will own the sky in cadence, nightly passes building light curves for billions of sources. That's perfect for flagging long, smooth lensing bumps. But Rubin's strength is also a blind spot. It needs a source to fluctuate. In the sparse star fields near the solar neighborhood, you just don't have the dense backdrops that bulge fields give you. Meanwhile, Roman will stare deep and long at crowded regions, measuring parallax across the telescope's own vantage in Earth's orbit. That separates compact dark lenses from stars more cleanly. But Roman's survey fields are chosen for microlensing yield, not for sweeping the whole sky for local drive-bys. If a rogue cuts across a quiet patch, Roman might never look. Even when you do catch a lensing event, the information is surgical. You get a mass estimate, a distance bracket, a proper motion on the sky. You don't get a beacon you can track forever. Once the alignment ends, the lens fades back into statistical darkness. Predicting its future path requires exquisite astrometry and luck with future background stars. For nearby rogues, backgrounds are sparse, so the next measurable alignment might be years, or never. Another reason they hide: confusion. Binary stars can fake lens-like light curves. Star spots can mimic slow drifts. Instrument systematics can push a centroid the wrong way. Teams spend months filtering false positives. A few percent of ambiguous events can swing your inferred dark lens population from rare curiosity to common but quiet. That uncertainty isn't just academic. It sets how wide we cast our net. Add the cruel geometry of gravitational focusing. A fast lens bends trajectories more when it's close, but it also spends less time in the zone where we could see signatures. High-speed halo rogues blaze through with fewer opportunities to accrete or to line up behind multiple stars. They're the stealth jets of the population, loud in gravity, silent in light, gone before you look. So we're scanning a keyhole for a bullet. Gaia is our ruler for tiny sky wobbles. Rubin is our heartbeat monitor for light curves. Roman is our precision scale. Radio arrays and X-ray monitors are the motion sensors on the walls. Each has blind spots, cadence gaps, magnitude limits. Stitch them together and you still miss most of the galaxy, most of the time. That's the psychological trap. Great tools make us feel safe, until a quiet pass reminds us coverage isn't the same as control. That's the stakes in one sentence. If our sensors can't flag a rogue early, warning shrinks from years to months to nothing. Which leaves one practical question. If one actually swings by, what does the pass look like from out where our comets sleep? Anatomy of a drive-by, through the outer solar system. Start far out, so far that the sun is just another bright point. The Oort Cloud isn't a shell of packed ice balls. It's a vast, thin fog, trillions of comets on slow, cold orbits stretching tens of thousands of astronomical units. A rogue black hole doesn't need to come close to stir it. Tides get there first. Gravity doesn't pull equally. It pulls harder on the near side than the far side. That gradient is the quiet alarm. At around 10,000 AU, you don't get fireworks. You get statistics. The energy of those distant orbits is tiny. A small nudge changes everything. Pass a 7 solar mass lens through that regime and the cloud feels it as a long, low tide. Some comets are lifted, some lowered. A few get pushed onto trajectories where the sun's pull tightens its grip. They fall inward not all at once, but over decades and centuries, like a storm swell that keeps sending waves after the wind is gone. Closer, around 1,000 AU, the geometry shifts from gentle tide to discernible tug. Here, the rogue's passage is fast, tens to hundreds of kilometers per second, but the gradient across the Oort Cloud fragments it touches is stronger. Numbers turn into events. A fraction of bodies tip into long ellipses with perihelia diving toward the inner system. If the intruder's path crosses at the right angle, you get a spike in comet injection that begins years after the closest approach and echoes for centuries. At 100 AU in the scattered disk in the outer Kuiper belt's fringe, the stakes feel personal. We have spacecraft out there. We also have large, slow-moving worlds with names and histories, Sedna-like objects detached and quiet. The rogue won't suck anything in. That's not how gravity works. It will pass, accelerate local bodies a bit, and leave. But a bit at those distances can mean ejections, captures, or gentle chaos. 1,000 tiny course changes that rewrite collision calendars long after the interloper is gone. Simulations tell the story better than metaphors. Set up a numerical experiment. Seed 10 million test comets in a realistic Oort Cloud distribution. Add planets. Then send a 7 solar mass object through on a hyperbolic path at 80 kilometers per second with a missed distance of 150 AU. Run it. What you see isn't an apocalypse. It's a redistribution. A small percentage is ejected entirely, trading the sun for the galaxy. A smaller percentage is dropped into long-period orbits with perihelia inside the planetary region. A vanishingly small subset gets captured into bound companions if the velocity and angle are just right, rare, but not impossible. Now add complications we didn't earn. What if the rogue is a binary, 2 compact objects gliding together? The tidal field gets lumpy, resonances creep in. A few test particles get unusually strong kicks when their orbital phases coincide with the binary's motion. Rare outcomes become slightly less rare. Still, the main story holds. Tides first, then scatterings, then a long tail of consequences. From a human vantage, the pass is anticlimax followed by patience. During the event, nobody on Earth feels a thing. No sky tear, no auroras, no global tremor. The accretion glow we'd crave likely doesn't appear. There's not much to eat that far out. The first hints arrive as numbers. A minor shift in the trajectories of known distant trans-Neptunian objects. A puzzling uptick in faint, long-period comets a decade later. Timing residuals in outer planet ephemerides that refuse to average away. Here, where the timeline stretches. A surge in long-period comets doesn't hit like a meteor shower. It rises as a background risk. Over 50 to 200 years, more comets with large perihelion distances get nudged into the inner system. Planetary defense pivots from near-Earth asteroids toward tracking cold visitors with long lead times and poor orbits. The night sky gets busier for survey telescopes. Civilizations don't get wiped. They get busier, then smarter, or unlucky if they ignore the statistics. The only real mistake is to treat a slow threat like it's far away. There's a quieter outcome hidden in the noise. Slight, cumulative orbit tweaks for outer planets are a constraint. High precision ranging to spacecraft at Saturn and beyond gives us daily truth serum on our gravitational model. A rogue that comes inside a few hundred AU leaves a tidal fingerprint in those residuals. If we don't see it, we can push the allowed mass distance box outward. That's how a drive-by becomes both a risk and a measurement. Meanwhile, local captures, if they happen, are stories for future astronomers. A tiny population of comets could end up loosely bound to the rogue for a while, then released with altered energies as it exits. That could seed asymmetric influxes decades later, adding structure to the comet shower that wouldn't be obvious without careful cataloging. It's tempting to ask about extremes. What if a pass hits at 100 AU dead-on? The solar system's architecture is resilient. Planets are deep in the sun's well. You'd see measurable perturbations in the Kuiper belt and scattered disk. You'd risk losing some minor bodies, and you'd boost long-period comet traffic for a significant chunk of time. But Earth doesn't get ripped from the sun. The atmosphere doesn't tear away. The danger is cumulative exposure to more impactors, not cinematic collapse. All of this loops back to warning. If a rogue crosses at 10,000 AU, the first signs are statistical and slow. At 1,000 AU, you might catch astrometric hints in outer planet data and plan for a century-scale comet uptick. At 100 AU, you D want probes retasked yesterday, outer sentinels measuring trajectories in real time, and a global plan to track new comets early. No suction, no roar, just gravity doing the quiet work that history remembers later. The odds, how likely is a close encounter? To weigh fear against facts, we need math that ties population to risk. The core idea is simple: how many rogues per volume, how fast they move, and how big a target you're drawing around the sun. Number density times velocity times cross-section. Then add gravitational focusing, because gravity fattens the target as objects speed by. Start with the geometry. Imagine a cylinder through space with the sun at its center. Any black hole passing through that cylinder with radius equal to our danger distance counts as a close encounter. If you set the danger radius at 1 parsec, about 206,000 AU, you're asking how often a rogue wanders within the broader outskirts of the Oort Cloud. Shrink it to 0.1 parsec, or even 1,000 AU, and you get stricter, scarier passes. The smaller the circle, the rarer the hit. Now plug in a plausible local density. Take a cautious estimate that gives you a handful of stellar mass black holes within a few dozen parsecs. Fold that into a characteristic speed, tens of kilometers per second for disk rogues, up to a few hundred for halo crossers. Multiply density by speed and by the area of your circle. Then correct for gravitational focusing, which effectively increases the radius because the sun's pull bends trajectories inward. Heavier, slower lenses are focused more. Faster halo objects shrug it off. So what drops out? For passes within 1 parsec, you get probabilities per million years that aren't zero. Over tens of millions of years, a brush at that distance becomes likely. Tighten to 0.1 parsec, roughly 20,000 AU, and the chance per million years shrinks, but across a billion-year horizon it still lands in the could happen bin. Bring it down to 1,000 AU, and the math gets stingy. On human timescales, it's negligible. On geological timescales, it sits in the long tail. Improbable in any given million years, not impossible across the deep past and future of the solar system. Here's a way to ground it. We already know stars pass close. Skal's star likely skimmed within about 0.25 parsecs some 70,000 years ago. Gliese 710 is projected to swing within roughly 0.6, 2 parsec in 1.3 million years. Those are luminous cataloged objects. They announce themselves. Dark rogues, if present in similar or slightly lower densities, would add a silent layer of flybys we wouldn't have counted. Most would still miss by large margins. A few would graze the comet cloud. Vanishingly few would thread the inner outskirts. The key difference is detectability, not inevitability. A bright passerby can be modeled for centuries. A dark one needs a specific alignment with a background star or a tidal whisper in our ephemerides. That's why the risk is asymmetric. On paper, the odds for stars and rogues within a parsec can be comparable. In practice, one is watched, the other is. Gravitational focusing nudges the numbers but doesn't flip them. At high speeds, say 200 kilometers per second, the focusing term is small. At lower speeds, 20 to 40 kilometers per second, it grows, especially for heavier lenses. That makes slow, disk-bound black holes slightly more likely to wander deeper into our chosen circle than naive geometry suggests. But the biggest lever is still the radius you care about. 10,000 AU sees more traffic than 1,000 AU by a factor of 100 in area, before focusing. Uncertainty is the hidden protagonist. Change the local density by a factor of 3, and the encounter rate follows. Tilt the velocity distribution toward faster halo objects, and you get fewer long interactions but more quick grazes. Assume a clumpy distribution, more rogues near spiral arms or lingering around old clusters, and your local odds swing with the sun's position along its galactic orbit. The tails of these distributions do the damage. Rare combinations of slow speed, high mass, and the wrong trajectory dominate risk, even if they barely affect averages. So where does this leave us practically? On human horizons, centuries to a few millennia, The chance of a rogue diving inside 1,000 AU is so small you can live your life happily and be right. On civilization horizons, tens of thousands of years, the odds of a pass within 0.1 parsec are small but non-zero, with consequences that play out through increased long-period comets rather than instant catastrophe. On geological horizons, millions to hundreds of millions of years, encounters within a parsec are expected, and deeper passes move from rare to plausible given enough time. That's why the plan matters more than the panic. Unlikely isn't safe, it's a wager. The sun has been circling the Milky Way for billions of years. If the dice get rolled long enough, the low probability boxes get checked. Our job is to drag the probabilities back into our favor by stretching warning time. Because the next reasonable question is, will it happen? If something is inbound and quiet, how do we see it with enough time to act? And if we can answer that, we turn anxiety into agency. The tell, microlensing and astrometric wobbles nearby. If something heavy and dark is inbound, the first clue probably isn't a roar, it's a twitch. A background star brightens by a few percent for a month. Its apparent position drifts by tens of microarcseconds, then slides back. That pairing, light curve plus tiny sky wobble, is the tell. It's gravity writing a forwarding address in pencil. Microlensing is the brightness bump. Astrometric lensing is the sideways nudge. Together, they let you solve for the lens's mass and motion without ever seeing it. Here's the dance. As the lens moves in front of a star, the star's image is distorted into unresolved arcs. The total light rises smoothly, peaking when alignment is tightest. Meanwhile, the centroid of the light on the detector shifts off the true position in a small ellipse. The size of that ellipse scales with mass and geometry. Measure both, and you're not guessing anymore. The catch is field density. Toward the galactic bulge, there are stars behind every stars. In our neighborhood, the sky is sparse. That's a problem if you're waiting for chance alignments. So the strategy changes. Instead of staring at one patch and hoping, you map a candidate lens's path across the sky and project it onto known background stars years ahead. That turns microlensing from serendipity into scheduling. If you can measure a dark lens's proper motion from an initial event, you can predict future grazes and be there with the right instruments. Gaia is the quiet hero here. It measures positions and motions for more than 1 billion stars with microarcsecond precision. That lets you see subtle centroid drifts when a lens crosses a line of sight. Not every star is bright enough. Not every cadence is perfect. But when the geometry lands, Gaia can pick up astrometric lensing even without a clear photometric bump. Those are the wobbles that whisper mass. Rubin helps from the ground by catching the long, smooth light curves in the time domain. Its nightly cadence paints brightness histories for billions of sources. If a star starts the slow climb characteristic of microlensing, Rubin will notice, flag it, and feed a live alert. That's your cue to swing higher precision eyes onto the field for astrometry. Gaia if it's in range, or small dedicated interferometers if you've got them. Roman closes the loop. From space, with stable optics and wide-field microlensing campaigns, it can do parallax. Watch the same event from a slightly different vantage across Earth's orbit and its own station, breaking degeneracies in mass and distance. Roman's specialty is packed bulge fields, but its precision scales to any planned overlap. If we've projected a rogue's path and there's a viable background star ahead, Roman can sit on it and weigh the lens in real time. Now local search is a different beast. In the bulge, you fish in a teeming pond. Near the sun, you're hunting along a predicted track where background stars are few. The playbook shifts to pre-computation. You take a candidate lens's proper motion and uncertainty, propagate it forward, and intersect that swath with star catalogs down to faint magnitudes. Every potential crossing gets a window and a probability. Most hit nothing useful. A handful line up cleanly. Those become appointments years in advance. False positives try to break your heart. Binary stars can mimic lens-like curves as spots rotate or as companions eclipse. Instrument systematics can push centroids around by just enough to look interesting, so you filter hard. A true microlensing light curve is achromatic. It doesn't change color, and symmetric in a specific way unless there's parallax or finite source effects. Astrometric shifts trace an ellipse with a known orientation relative to the light curve. If you don't see those fingerprints together, you don't call it dark. When it works, the payoff is leverage. With mass and motion in hand, you can project a trajectory out of the sky and into space, a three-dimensional path with error bars. That lets you answer the only question that matters. Does this thing cross the outer solar system's danger zones within a useful time frame? Most won't. But if one does, you're not blind anymore. You can retask radio dishes for wakes, ping X-ray monitors for transients, and reset the priority list for outer planet tracking. There's a human side to this that never shows up in the plots. Someone has to watch the alerts at 3 a.m., decide whether a curve is clean, and burn precious telescope time on what might still be a dud. Someone else has to live with a calendar full of maybe alignments 3 years out, knowing clouds or a gyro hiccup can kill the shot. And still, the work is addictive, for one reason. Every correct mass and proper motion you add to the ledger tightens the map. It shrinks the space where a rogue could hide and still surprise us. That's not just science. That's time banked for later, and time is the only defense we can manufacture. Gravity's fingerprints on the solar system. While alerts blink over distant stars, the solar system keeps its own quiet logbook. Gravity leaves fingerprints here too, subtle, precise, impossible to fake if you know where to look. If a rogue brushes past, the first proof might not be a light curve. It might be a number that refuses to fit. Start with the planets. We don't just know where Jupiter and Saturn are, we know them to absurd precision. Radio ranging to spacecraft, long baseline tracking, laser timing reflected in the web of ephemerides. It all adds up to a metronome. When something massive sweeps nearby, it won't jerk Jupiter out of orbit, but it will tug differently on Jupiter and the Sun than on Saturn and the Sun. That difference shows up as a tidal pattern in the residuals, the tiny mismatches between predicted and measured positions. If those residuals shift in a way that fits a passing mass, you've got a whisper of an intruder. Meanwhile, far beyond Neptune, the Oort Cloud stores kinetic energy like a flywheel. A rogue's tide nudges that energy, changing the fates of trillions of dark comets. The impact on us is delayed. Decades after the closest approach, you'd see a slight, persistent uptick in new long-period comets, especially ones arriving from a common Great Circle band on the sky. That anisotropy is the clue. Random background infall is scattered. A tidal injection carries a directional memory of the passer's path. Now constraints cut both ways. Cassini's ranging to Saturn was so good it fenced off a lot of fantasies, fifth forces, hidden planets, and yes, big invisible masses skulking just outside the Kuiper belt. New Horizons and Juno add more posts to that fence. If a 7 solar mass object had strolled within a few hundred AU in the last couple of decades, the tidal imprint on those datasets would be loud by now. We don't see it. That pushes the allowed mass-distance combinations outward and tells us what hasn't happened recently, which is its own kind of comfort. But there's a threshold game here. How close, how heavy, how fast before the alarms trip? For a Jupiter mass intruder, even at hundreds of AU, today's ephemerides would flinch. For a multi-solar mass rogue, the range extends farther. A passage inside 1,000 AU would draw a distinct, low-frequency tide across the outer planets. Below that, the pattern strengthens and resolves into something you can fit with a model. A gradient consistent with a transient mass on a hyperbolic path, not a bound planet. The signature is time-structured, rising as it approaches, peaking around closest passage, then fading with a memory written into comet statistics. Here's the part that's easy to miss. Those same ephemeris residuals can guide a search. If you see a consistent tidal mode, you can invert it into a sky direction with uncertainties, then comb that sector for astrometric lensing opportunities. The solar system becomes its own detector, pointing our telescopes at where the sky's background might twitch next. Even a hint can concentrate resources. More deep drilling with Rubin in that strip. Roman parallax campaigns bookmarked if any source lens pairs line up. Radio arrays tuned for faint wakes along the predicted track. And yes, wakes matter if the rogue finds fuel. The stealth route isn't perfect. A black hole marching through denser interstellar patches drags gas, heating it just enough to glow in radio or soft X-rays. On paper, Bondi accretion in the local hot bubble is tiny, but the galaxy isn't uniform. A puff of colder gas, a filament, a loose debris sheet in the scattered disk, any of those could spike the emissivity for months to years. If a tidal signature points to a likely corridor, a parallel watch for transients in that lane buys you redundancy. Astrometry says something heavy passed. A radio whisper says it's still chewing. None of this happens without clean baselines. That means outer planet tracking with the discipline of a heartbeat study. Regular, precise, boring until it is. It means pushing for laser ranging improvements, not just to the moon but to deep space transponders, so the web of gravitational truth tightens. It means mining occultations of distant Kuiper belt objects for small, systematic shifts in their ephemerides. Tiny deflections that, when stacked across dozens of bodies, add up to a coherent tide. If you want a human moment, it's this: a planetary dynamics team staring at a residual plot where the points refuse to lie flat. Someone suggests solar radiation pressure. Someone else blames a spacecraft thermal model. Weeks pass. The bump persists. Then a fit with a transient quadrupole tide lines up better than any systematics model. The room goes quiet because the simplest explanation is no longer inside the spacecraft or the math. It's out there. In the aftermath of any real pass, the solar system keeps talking. New comets appear from a preferred band. The Kuiper belt's faint families show slight reshuffles. Long integrations of outer bodies pick up minuscule phase drifts that match a once-only shove. Piece by piece, the mosaic resolves. Not a Planet 9, not a statistical fluke, but the fingerprint of a dark mass that came close, didn't linger, and left us with homework for 100 years. When the invisible starts to eat. There's one way a quiet rogue stops hiding. It finds fuel. The moment gas meets gravity, the dark turns into a beacon. Not a quasar roar, more like a flare on a lonely road. And here's the catch. By the time it glows, it might already be inside the zone where warning time matters. Start with conditions. Space near the sun isn't empty, but it's thin. The local bubble is hot and sparse, a few atoms per cubic centimeter moving fast. Bondi accretion from that soup is slow. A 7 solar mass black hole with a typical disk speed drift barely sips. You get a faint radio whisper at best. But the galaxy isn't uniform. Filaments of colder gas thread the plane. Tiny clouds drift. The scattered disk holds debris, dust, and outgassed tails from ancient comets. A rogue punching through any of that fattens its meal. When it eats, the physics is simple but unforgiving. As gas falls in, it heats, radiates, and slows, forming a bow shock upstream and a wake downstream. Magnetic fields twist, electrons spiral and spit out synchrotron radio. Close to the black hole, if the flow gets dense enough, you see soft X-rays. The spectrum depends on speed and supply. Fast passage, low density. Radio first, weak X-rays. Slow passage, denser pocket. An X-ray transient that pops up with no star in sight. That's the moment most viewers find out, right when the clock is already ticking. This is where telescopes matter. Radio arrays like Meerkat, and soon, the sky can map faint, elongated wakes, arc-minute-scale smudges moving with the lens. They're dim, but they move, which helps. X-ray monitors sweep wide and shallow, catching new sources all the time. Flare stars, cataclysmic variables, magnetars on a bad day. A rogue would join that pile as an unclassified transient with no optical counterpart. It's the missing star that gives the game away. Bondi rates are the metronome underneath. Feed density sets luminosity. In the local bubble, you might get 1028-1030 erg-s, barely a blip, detectable only nearby with dedicated searches. Slide into a cooler, denser cloud, and you can jump orders of magnitude. Suddenly, The source is bright enough for all-sky X-ray surveys to ping. You still won't see a point of light in the optical. You'll see motion, proper motion that doesn't match a star and a spectrum that says hot gas, no photosphere. Here's a micro-story from the future we keep planning for. A duty astronomer at an all-sky X-ray survey flags a new source near the ecliptic. Bright, soft, no known optical partner down to deep limits. They tag it unidentified transient and push an alert. 2 nights later, a small radio dish reports a faint, elongated source offset by a few arcseconds, consistent with a bow shock. That's weird. Someone cross-matches both positions with Gaia. Nothing there above the noise besides background specks. The chatter starts. Within a week, the fits begin. Assume a compact object. Fit the proper motion from the survey cadence. The source is moving. The brightness doesn't flicker like a magnetar or a flare star. The radio elongation stays aligned with the motion vector. If it were a neutron star, you might expect a different spectral slope, maybe pulsations. You don't see them. Meanwhile, Rubin throws in. Nearby stars show no variability consistent with an eclipsing binary contaminant. The field is clean. The team breathes in. They try an accretion wake model on a 7 solar mass lens crossing a light, cold cloud. It matches too well. When the invisible starts to eat, detection range leaps. A radio wake can be tracked for months if the supply persists. X-rays come and go with density. If the rogue is inbound, those months matter. You can project a path, tighten uncertainties, and coordinate astrometry to search for upcoming microlensing of background stars along that track. Suddenly, the rogue isn't a ghost. It's a moving target with a schedule. But there's a cruel timing. Fast passage means short meals. A halo crosser at 200 kilometers per second pierces a cloud in days to weeks. It lights, then fades. A disk drifter at 30 kilometers per second lingers, glowing for months, maybe years if the cloud is thick. Speed decides your warning window. Fuel sets how loud the alarm rings. And here's the human beat. The moment a team whispers dark accretor, everything speeds up. Telescope time gets begged and borrowed. Proposals are written overnight. A Slack channel fills with plots and bad jokes. Someone calculates the expected comet injection if the path clips the scattered disk and quietly swallows hard. Not because disaster is certain, but because now there's a clock. The object we couldn't see has started to announce itself, and the announcement might already be late. So we change posture. We treat every unidentified X-ray transient without an optical host as a potential rogue until proven otherwise. We build radio follow-ups that can catch bow shocks and measure proper motion. We wire these alerts into the same pipelines that watch for astrometric wobbles. Because once the dark starts to eat, the smartest move is simple. Turn its appetite into our early warning. Mass, spin, and speed, the parameters that matter. Now that we've heard the first radio whisper and seen how a wake can betray a passerby, the next question is brutal in its simplicity. What kind of rogue is it? 3 dials set everything that follows: mass, spin, and speed. Change anyone, and the timeline, the damage radius, and even our ability to track it all shift. Start with mass. Gravity scales with it, and so does the Einstein radius in lensing. The bigger the mass, the wider the area over which a background star will wobble and brighten. A 2 solar mass compact object can lens, but the light curve is shorter and the astrometric shift smaller. A 7 solar mass lens stretches the event, hands you a clearer ellipse, and leaves a stronger tidal signature if it comes near the solar system. In the outer reaches, mass doesn't rip planets free, but it does raise the chance that Oort Cloud particles get bumped into long ellipses or ejected entirely. The heavier the lens, the larger that perturbation volume, the region where tides are strong enough to matter. Mass also buys you gravitational focusing. A heavier lens fattens the effective cross-section for close approaches, especially if it's moving slowly. That makes a high-mass, low-speed rogue the one you worry about for deep incursions. It spends longer in the danger zone, bends trajectories harder, and gives more chances for background stars to align along its path so we can catch it again. speed pulls in the opposite direction. A fast halo crosser, 200 kilometers per second, flies like a bullet. It's harder to catch with microlensing because each alignment is brief. The astrometric ellipse is crossed more quickly, and accretion signatures are fleeting. The odds of it chewing on a cloud long enough to light up are lower. But speed shortens the interaction with our outskirts too. The tide rises and falls faster, which can blunt some of the cumulative chaos. You trade warning time for a thinner slice of exposure. A slow disk drifter, 20 to 40 kilometers per second, gives us more of everything. The microlensing light curve lingers. Roman and Rubin can track it with fewer missed nights. Gaia has more epochs to map the centroid ellipse cleanly. If it eats, it glows for months, not days. And if it brushes the Oort Cloud at a few thousand AU, the tidal push is applied over a longer arc, nudging more objects through small changes that add up. Slower speed also lets gravitational focusing do its work, bending the rogue's path slightly deeper into our danger radius. Spin is the subtle one. At AU scales, frame dragging is negligible. The Kerr geometries twist matters near the event horizon, not out where comets drift. But spin still carries information. High spin hints at a collapse without much mass loss, or a binary history that torqued the hole up before it was ejected. Low spin points to different origins, fallback supernovae that bled angular momentum into expelled shells, or multiple minor mergers that averaged out. For our purposes, spin is a fingerprint, not a lever. It doesn't change the Oort Cloud math, but it changes the story of where this object came from and how many siblings might share its kinematics. Origins matter because they correlate with speed and environment. Direct collapse black holes in the disk tend to inherit disk motions and stay slow. Natal kicks from asymmetric supernovae can launch remnants into high-velocity orbits that thread the halo. Cluster ejections carve out a middle case, objects slung free with speeds that depend on the cluster's internal violence. Each channel paints a different risk map. Disk-borne, slow rogues are the lingering ones, harder for us in the long term. Halo streakers are stealthy but brief. Here, where the human work pays off. Once we measure mass and proper motion from a microlensing event, we can fold in the wake brightness, the presence or absence of X-rays, and even hints of polarization in the radio to constrain speed through the medium. If the radio bow shock is wide and faint, the lens may be moving faster. If it's compact and bright at the same density, slower. Combine that with astrometric parallax and you can box the velocity vector in 3 dimensions instead of 2. Suddenly, you're not arguing in the abstract. You're tuning the dials with data. Then we project forward. A heavy, slow lens with a path that skirts 5,000 AU gets a red flag. We accelerate ephemeris monitoring, set up occultation nets for trans-Neptunian objects along the predicted corridor, and schedule deep drilling fields for Rubin to catch any future microlensing along the track. A lighter, faster lens with a miss at 50,000 AU still gets watched, but the plan shifts. More emphasis on comet statistics years from now, less on immediate solar system fingerprints. Mass also shapes the capture tail. Only rare geometries trap debris, but if it happens, a heavier lens holds onto companions a bit more readily during the pass. That could seed structured comet showers with identifiable timing over decades. Again, not a catastrophe, but a recognizable pattern that tells us the mass dial was set high. Spin won't alter that capture rate, but it will tempt theorists with origin stories when we publish. Underneath all this, one more parameter hides in plain sight: environment. Speed through gas, density of what it's crossing, even the magnetic texture of the interstellar medium. All of it modulates how loud the rogue will be when it eats. A fast, heavy lens in hot, thin plasma can be quieter than a modest lens swimming slowly through a cold filament. That's why we fuse sky surveys with 3D dust maps and gas surveys, predicting brightness along a path like a weather forecast for a storm we can't see. So when we ask what matters, the answer is layered. Mass sets the strength of the invisible hand. Speed sets the clock. Spin signs the origin card. Together, they decide whether this is a months-long chase with early warning or a brief whisper followed by decades of aftermath. And they point to a final lever on our side, better tripwires that catch each dial earlier and read them cleanly. The new tripwires, Roman, Rubin, Gaia, and Ska. Everything we've learned points to one truth. We need earlier alarms, not luck systems. The next wave of instruments gives us tripwires we've never had, each tuned to a different whisper from a dark lens. Stitch them together and we stop hoping for serendipity and start planning on detection. Start with Roman. It's built for microlensing parallax from space, stable optics, wide field, and long dwells on dense star fields. In the bulge, Roman will catch thousands of lensing events with exquisite light curves. But the killer feature is parallax, observing the same event from a slightly shifted vantage and across Earth's orbit breaks the mass-distance degeneracy cleanly. Heavy lenses pop out of the fit. That turns maybe a compact object into this many solar masses, moving this direction. Roman won't patrol the entire sky, but it will build a definitive catalog of dark lenses with measured masses and proper motions. Raw material for projecting tracks years ahead. On the ground, Rubin is our cadence engine. Nightly sweeps build light curves for billions of sources, catching the slow, symmetric bumps that scream microlensing. Rubin's strength isn't precision per point, it's relentless repetition. If a nearby rogue crosses a sparse field and still manages to lens a background star, Rubin will raise the flag early, feed an alert, and give us a real-time schedule. Better yet, deep drilling fields can be aimed along predicted corridors from Roman's catalogs, increasing the odds of catching repeat alignments as the lens moves. Gaia keeps playing the long game, but the sequel is key. Gaia NIR, the proposed near-infrared upgrade. The Milky Way hides half its background behind dust. Near-infrared astrometry pierces that smog, doubling the star fields available for lensing tests and improving centroid measurements where extinction killed them before. Micro-arcsecond astrometry in the NIR means more chances to see that telltale elliptical wobble in regions Roman and Rubin can mine for light curves. Even without the upgrade, Gaia's extended baseline sharpens proper motions, turning ambiguous nudges into clean ellipses. With Gaia NIR, the wobble map expands into lanes we couldn't see. Then there's radio, the Ska era. A quiet rogue isn't always dark in radio if it's plowing through gas. Ska's sensitivity and resolution make faint, arc-minute scale bow shocks visible at distances where older arrays saw only noise. More important, Ska tracks motion. A wake that moves across the sky week by week can be fit for speed and direction, independent of optical counterparts. You cross-match that vector with astrometric candidates and microlensing tracks, and suddenly the picture locks. A heavy lens moving this way, lighting this gas, on course for that strip of background stars. All sky X-ray monitors add the flashers. EROSITA's legacy and its successors sweep for soft transients. Most are mundane. The ones with no optical hosts, repeating proper motion and radio wakes become immediate suspects. We fold those alerts into the same pipelines that watch for microlensing, so every unidentified X-ray transient near a predicted corridor gets fast radio follow-up and astrometric scrutiny. When the invisible eats, we hear it. And when we hear it early, we get to choose our next move instead of react to it. Data fusion is the pivot from hope to plan. Picture an engine that ingests Roman light curves and lens parallax fits, Rubin alerts, Gaia astrometric residuals, Ska radio maps, and X-ray transient catalogs. It scores candidates on dark lens likelihood, then projects trajectories with error bars, intersecting those paths with deep background star catalogs. Outdrop appointment windows, dates, coordinates, and expected signal strengths for probable relensing events or bow-shock passages. Each success tightens the priors, sharpening the next round. This isn't magic, it's logistics. Coordination wins or we miss windows. Roman's bulge seasons are set, Rubin's deep fields can be steered. Gaia's cadence is what it is. Ska time is precious. So we build a shared alert standard where a mass-bearing Roman lens immediately spawns Rubin field priorities, Gaia watchlists, and Ska target of opportunity triggers. We pre-approve programmatic interrupts for dark lens high-confidence flags, so no one is writing proposals at 3 a.m. while the event peaks. Timelines matter. Roman ramps mid-decade. Rubin is already seeding the sky with alerts. Gaia's baseline lengthens each year. Ska phases on line region by region. The gap is closing, but it isn't closed. That's why we add cheap tripwires now. Small optical arrays to dense monitor predicted corridors. Community radio dishes scripted to chase X-ray transients automatically. Occultation networks listening for subtle, coordinated timing shifts in distant Kuiper belt, objects along suspect lanes. There are limits we won't wish away. Roman won't watch the whole sky. Rubin needs a background star to fluctuate. Gaia's precision fades for the faintest sources. Ska can't spend weeks on a ghost without proof. But together, the blind spots don't overlap perfectly. One instrument's weakness is another's strength. Parallax plus cadence plus micro-arcsecond wobble plus moving radio wake, that's a 4-lock safe. If a rogue trips all 4, we're not surprised later. We're scheduling its exits. Here's the point. We stop scanning a keyhole for a bullet when we put sensors on all the doors. Roman weighs, Rubin watches. Gaia and IR measures the twitch in dusty lanes. Ska hears the wake. The next inbound won't announce itself. We'll announce it first. Scenario: a near miss within 1,000 AU. We didn't start with a siren. We started with a residual that wouldn't die. An outer planet dynamics group saw a low, slow tide in the ephemerides. Tiny, coherent drifts that fit no thermal model, no missed gravitational harmonic. The fit that worked best was ugly and simple, a transient quadrupole, as if something heavy had brushed the system's edge and kept going. 3 days earlier, Rubin had flagged a long, clean microlensing curve in a sparse field, achromatic, symmetric, slow. Gaia's centroid data sketched an ellipse. The inferred lens mass landed near 7 suns. The proper motion pointed across the ecliptic, and the distance bracket slid closer than anyone liked. When the two teams finally talked, the vectors roughly agreed. If the track held, periapsis would miss the sun by about 1,000 AU in 18 months. The first week was denial and math. Could spacecraft systematics fake the tide? Could a binary star near the line of sight twist Gaia's centroid? Teams traded data like shared oxygen. Rubin's curve was textbook. Gaia's ellipse matched. The outer planet residuals kept their shape through multiple observations. Someone wrote "candidate inbound" on a whiteboard and underlined it hard enough to squeak. Timeline clicked in. Step 1. Announce internally, freeze ephemera solutions, and widen the watch. Step 2. Pre-compute the lens's sky path 6 years forward and 6 years back, cross it with deep star catalogs, and publish appointment windows for possible relensing events. Step 3. Ping radio and X-ray networks. If it chewed, even briefly, we wanted wake maps and soft photons. Markets heard a rumor before policy did. A speculative thread about dark object near solar system hit a forum and bled into headlines. Space stocks bumped. Insurance models didn't know what to do with century-scale comet risk. Agencies scrambled to get the story right in public. No collision, no gravity well sucking planets away. This was a near miss in the outer dark with long-tail consequences. Calm, precise language fought with fear. It always does. The lesson lands fast. Clarity beats panic, but only if you speak first. Meanwhile, engineers made lists. Voyager 1 and 2 were aging but still talkative. New Horizons was healthy, far out, and in the general quadrant of the predicted passage. A plan formed to retask all 3 as sentinels, tighten ranging schedules, refine plasma and dust monitoring, and reorient whenever possible to map subtle field changes as the rogue's tide rose and fell. Every deep space transponder became a metronome. Rubin shifted a deep drilling field onto the projected corridor. Roman slipped a target of opportunity into its bulge campaign to catch a predicted relensing 2 months out, which would slash the trajectory error bars. Gaia marked the track on its internal watch list, squeezing extra precision where cadence allowed. Sky scheduled short, repeating snapshots across the lane, hunting for a radio wake drifting with proper motion. Coordination bled into policy. Who owns the early warning narrative for a non-luminous gravitational hazard? The IAU set up a cross-commission task force. Planetary defense offices wrote an interim protocol. Alerts, uncertainty bands, timelines, and what near-miss meant in practical terms. The biggest line was simple: no action needed for Earth safety now. Prepare for elevated long-period comet discovery rates over decades if the path and mass held. In labs and basements, a dozen micro teams spun up comet injection simulations tuned to the updated trajectory. The consensus stabilized. At 1,000 AU and 70 kilometers per second, the Oort Cloud would take a measurable nudge. Over the next century, the flux of long-period comets reaching the inner system could climb by a factor of 2 to 3 above background for a while, peaking decades after closest approach. Not a firestorm, an elevated background risk that demanded better surveys, earlier orbit solutions, and more deflection options ready on the shelf. A planetary defense microstory unfolded in a single exchange. A junior analyst slid a plot across a table, projected detections of long-period comets under a near-miss scenario, with error bands wide but rising. The room went quiet. No panic, just a reordering of priorities. Funding requests shifted toward follow-up capacity and orbit determination for cold visitors. The goal wasn't heroics, it was time. Public messaging settled on 3 sentences and stuck to them. 1. A dark, heavy object will pass the sun at roughly 1,000 AU. This is far beyond the planets. 2. It cannot pull Earth or any planet from orbit. Gravity doesn't work like suction. 3. The main effect could be more long-period comets decades later, and we're upgrading the Sky Watch to meet it. Simple beats sensational when the goal is keeping people informed and engaged. As the date approached, numbers replaced nerves. Roman nailed the parallax on the predicted relensing. Mass tightened to within 20%, the proper motion vector narrowed. Gaia's astrometric ellipse from the second background pass agreed. Ska saw no sustained wake, no dense cloud meal, just a whisper at the edge of detectability. That was good news. Less fuel meant less glow and no drawn-out accretion phase. Closest approach came and went with nothing to feel. The tide peaked in the residuals exactly when the fit predicted. New Horizons logged a faint, expected change in the dust environment that could have been coincidence, but the timing matched the model's leading edge. The rogue slipped on, outbound, dim as it arrived. Then we waited and worked. Rubin and its partners tuned search pipelines for long-period comets, bias-corrected for the new cadence, and shared orbits fast. Ephemeris teams watched the residuals settle back to baseline. The predicted comet flux curve sat on calendars like a deferred storm forecast, not certain but likely. The near-miss didn't end anything. It started a 100-year project. What changed wasn't fate, it was posture. Agencies kept the early warning protocol active. The Roman Rubin Gaia SKA braid stayed tight. Outer sentinels got permanent roles in the timing web. And somewhere in a Slack channel with a tired name, someone posted the plot that mattered. A residual flattening back to quiet, followed by a horizon line labeled next probable lensing along track, 2031. We had an address. We had time. And the audience had a reason to come back for the next update. Worst case, a pass through the Kuiper belt. Here's the hard edge of the scenario. The track migrates inward, and instead of 1,000 AU, the rogue's hyperbola threads the Kuiper belt itself. No impact, no capture of planets, but the outer architecture takes a punch. The stakes jump because we've built instruments out there, and because the Kuiper belt isn't empty. It's a city of slow movers with fragile spacing. Dynamics first. A multi-solar mass lens racing through at tens of kilometers per second doesn't yank Pluto into the void. The sun's grip still dominates. What it does is inject energy and angular momentum asymmetrically. Dwarf planets, resonant trans-Neptunian objects, scattered disk bodies, they all feel a differential tug. Some are raised into higher eccentricity paths, some are dropped into crossing orbits, a fraction are ejected entirely. The belt's neat resonant chains loosen. Families blur. Long-standing orbital relationships tilt just enough to start new collisions decades and centuries later. Think of a crowded roundabout. One truck barrels through the outer lane without stopping. Nobody gets picked up by the truck, but a lot of drivers swerve, brake, or bump fenders. That's the Kuiper belt under a close pass. No suction, lots of near misses that turn into delayed fender benders. The most sensitive are the loosely bound, high eccentricity bodies at the belt's fringe. The densest swarms near resonances with Neptune can get stirred, redistributing members across inclination and eccentricity space, in ways you can diagnose years later. Collision cascades are the messy part. You don't get a firework on the day of passage. You get a probabilistic uptick in low-velocity impacts as newly misaligned orbits start crossing. Each collision grinds big objects into smaller fragments, and the cascade multiplies surface area. Dust goes up. Over years to decades, the Kuiper belt's dust production spikes, feeding a brighter, thicker outer zodiacal cloud. Infrared backgrounds inch higher. Thermal noise creeps into instrument baselines. Observatories feel it before the public does. Calibrations deviate, and pipeline teams mutter about unexpected sky brightness at long wavelengths. Now fold in infrastructure. New Horizons, if it's in the lane, rides a shallow tide. Ranging stays king. Tiny Doppler shifts map the gravitational gradient as the rogue approaches and recedes. Communication links aren't torn, but dust hazards rise. Even a small increase in micron-sized grains along a trajectory raises the risk profile for high-speed dust hits on spacecraft radiators and star trackers. Mission ops rethink pointing strategies, add autonomous dust avoidance modes, and tighten safe modes around the predicted peak of the dust flux. Science payloads become opportunistic. A spacecraft with a plasma instrument and a dust counter turns into a fly-through lab for the belt's response. If the rogue is feeding, a faint radio wake could thread the same region. Coordinated sky snapshots try to catch it. Meanwhile, Rubin leans hard into occultation campaigns, watching distant stars for brief blinks as reshuffled KBOs slide in front. Those blinks map where mass has moved, object by object, better than orbit fits alone. What about Earth? The danger is still time-shifted. Increased scattering in the outer belt and disturbed scatter disk populations feed more pathways inward, seeding an elevated flux of long-period and high-inclination comets. That's not an extinction switch. It's a background rise in targets for planetary defense. We'd expect more distant comets detected on elongated, poorly constrained orbits, with warning times dominated by discovery cadence. The immediate climate doesn't change because a black hole passed far beyond Neptune. Winters aren't pulled colder by some gravity trick. The risk is impact statistics over decades, small numbers, big consequences if unaddressed. Reality check matters here. Even a pass threading the Kuiper belt is rare in deep time, and the solar system is robust. Planetary orbits are stable. Tidal energy from a brief passage doesn't couple efficiently to their motion. The damage lives in the debris, distributed, delayed, detectable. It's stress, not collapse. A few dwarf planets get measurable orbital element shifts. Families of KBOs show new V-shaped spreads in size, frequency space from fresh collisional production. Dust brightens the ecliptic's far reaches. That's the worst-case signature, not a ripped sky. The response is as technical as it is calm. We harden outer missions against dust and replan trajectories through less crowded regions if possible. We boost sky coverage for long-period comets and invest in rapid orbit determination to buy months, not weeks. We thread a denser net of occultation observers to track KBO reshuffles. And we keep the public line honest. This isn't a doomsday pass. It's a messy nudge that makes our job harder and makes early warning more valuable. Here's the twist that helps us. Messy leaves clues. The Kuiper belt's reshaped orbits, the dust uptick, the anisotropic arrival of new comets, each is a timestamp of the rogue's path. Even as we absorb the risk, we learn the trajectory better, back out the mass more tightly, and turn the worst pass into a map for the next one. Building a real early warning system. If the worst case leaves a map, the smart move is obvious. Build alarms that hear the first whisper, not the aftermath. Time is the only currency that matters. So we design a system that turns scattered clues into weeks, months, even years of lead. Start with continuous astrometry. We lock in a disciplined cadence on outer planet ranging. Juno, New Horizons, any deep space transponder willing to carry a clock. Tie them with laser links where possible, push for next-gen transponders that beat current noise floors and publish residuals in near real time. That baseline is our seismograph for tides. When it wiggles, we pivot fast. Next, deepen microlensing where it counts. We keep Rubin's cadence relentless but add targeted corridor drills. Higher frequency visits along predicted lanes from Roman catalogs and any inbound vectors hinted by ephemeris tides. We seed small, dedicated telescopes to stare continuously at those strips, handing off the night across longitudes so we don't miss the most telling hour of a long, smooth curve. The aim isn't more pretty light curves. It's earlier flagging of a heavy lens with a clean fit. X-ray and radio watches become the motion sensors. We formalize an alert class for unhosted transients, bright soft X-rays without optical counterparts flagged within minutes. Automatic radio follow-ups scan for moving, elongated wakes and measure proper motion. We standardize the metadata so one click pulls spectrum, sky motion, and confidence on compact object accretor. If the wake is there, we have a target that moves. If it isn't, the null still narrows what fuel the intruder is likely to see. Now add beacons in the outer dark. We upgrade laser ranging to the moon today, but the bolder step is trans-Neptunian trackers, small, cheap probes seeded into high, stable orbits beyond Neptune, each with precision clocks and retroreflectors. They don't do much, just report their positions obsessively. Scatter a dozen and you've put GPS markers in the tide. A passing mass tugs them coherently, and the phase of that tug tells you direction. It's a quiet, persistent detector made of patience and ping. Occultation nets tighten the mesh. Amateur and pro teams already catch Kuiper belt objects blinking out stars. We scale that with coordination software, low-cost high-speed cameras, and predictive path tools that digest the latest ephemerides. When a corridor looks hot, we aim the net there. Subtle, consistent shifts in timing across multiple occultations become a stacked tide signature long before comets arrive. Crowd power isn't a slogan, it's a multiplier. We open the alert pipeline, Rubin, Roman, Gaia, X-ray, radio, and build a citizen science layer that classifies light curves, hunts symmetric bumps, and flags anomalies in residual plots. People are good at patterns. We feed them training sets, score reliability, and route high confidence finds to pros with the keys to big telescopes. The payoff is speed, a flagged candidate in minutes instead of overnight. None of this works without policy. We need a protocol for dark gravitational hazards. Who issues alerts? What thresholds trigger a public statement? How uncertainty is framed so markets don't invent stories. We write a standard that includes 3 essentials: the current best mass distance, velocity estimate with error bars, a plain language impact horizon, and the next measurement that can shrink uncertainty. Then we stick to it, even when social media boils. Data fusion is the heart. We build the Rogue Alert Hub, a live engine that ingests astrometric residuals, microlensing alerts, X-ray transients, radio maps, occultation timings, and outer-probe ranging. It assigns each candidate a dark lens likelihood score, projects 3D trajectories with uncertainties, intersects them with star catalogs to schedule relensing, and simulates Oort Cloud response in the background. When confidence crosses a threshold, the hub automatically drafts observation requests. Rubin deep drill commands, Roman targets of opportunity, sky snapshots, Gaia watchlist flags. No waiting for heroics. The choreography is scripted. Engineering follows the choreography. Outer sentinels get firmware that prioritizes ranging and dust sensing when a corridor alert pings. Ground telescopes reserve interrupt time for dark lens high tags. X-ray monitors keep a buffer so the last hour before an alert is saved. SCA and Pathfinders pre-approve short, repeating blocks for moving, faint sources. The theme is pre-commitment. You don't negotiate with time after the clock starts. And we test everything. We run drills on simulated candidates, fake microlensing curves injected into Rubin streams, synthetic astrometric ellipses, mock X-ray transients, then watch the pipeline respond. We measure lag, loss, and false positives, tune thresholds, and publish the latency. If a rehearsal takes 2 days to lock a vector, we know we're not ready. We shave it to hours. Finally, we measure success in negative space. Months with no alerts aren't wasted if the baseline's tight. Each null pushes the mass distance box outward. Each clean relensing refines how we predict the next. And when something does cross a line, the system doesn't panic. It does what it was built to do. Buy time, turn a ghost into a track, and turn a track into a plan. Where rogues come from. To understand the next pass, we need to rewind to the births and breakups that launched dark wanderers in the first place. Black holes don't just appear in empty lanes. They inherit motion and momentum from violent family stories. One path is supernova fallback. A massive star blows its outer layers, but the blast isn't clean. Some of that matter stalls, falls back, and pushes the core over the edge into a black hole. The explosion can be lopsided. That asymmetry gives a kick, a few tens to a few hundred kilometers per second, flinging the remnant onto an orbit that might vault it out of the disk into the halo. Those kicks write speed across the sky. Another path skips the fireworks. Direct collapse is simpler. The star's core can't hold, there's little mass ejection, and the whole thing slides into a black hole with minimal kick. Those remnants tend to keep the slow drift of their birthplaces. If they formed in the Milky Way's thin disk, they move like disk stars, slower, with orbits that hug the plane. Quiet births make quieter rogues, and those are the ones that loiter near us longer if they ever wander close. Clusters contribute a different kind of violence. In dense young clusters, massive stars die in packs. Their remnants, black holes and neutron stars, sink toward the center and start three-body brawls. Gravitational slingshots fling losers out at escape speeds. You don't need supernova asymmetry. Dynamics does the work. Ejected black holes leave the cluster on trajectories that launch them into the field with speed set by the cluster's depth. Some end up as the high-speed streakers we call halo crossers. Binaries complicate everything and explain a lot. Massive stars love company. When one collapses, the orbital dance can break. A moderate kick in the right direction unbinds the pair, sending both partners off on new, skewed orbits. If both stars are massive, you might get two compact remnants over time, each launch writing its own line through the galaxy. The breakup is the mechanism that populates the halo with remnants that didn't start there. Spin rides along as a clue. High spins often trace direct collapse or accretion histories in tight binaries before ejection. Low spins hint at supernovae that carried angular momentum away. We don't measure spin at solar system scales, but populations do. If a candidate we weigh by lensing sits on a track shared by many similar mass lenses, and their velocities cluster around disk values, that leans toward quiet, direct collapse births in the plane. If we see a wide velocity spread with many at hundreds of kilometers per second, cluster ejections and kick-heavy supernovae take the lead. There's archaeology in the sky if you know where to read it. The Milky Way's spiral arms mark where massive stars formed recently. Associations and superbubbles point to where they died. Map those past nurseries and you get corridors, regions where you expect more remnants, including dark ones. The sun orbits and bobs through the plane, crossing arm segments every few 100 million years. That means our background risk isn't uniform over deep time. Some epochs were statistically hotter, some cooler. depending on where we sailed relative to old birthplaces and their outbound debris. Halo populations smear the risk across the whole sky, but even there, anisotropy sneaks in. The stellar halo carries streams, tidal shreds of old clusters and dwarf galaxies. If those progenitors birthed black holes, their remnants follow the same great circles. A rogue on one of those streams isn't random. It's on a highway with others, which slightly raises the chance of multiple, widely spaced flybys with similar kinematics over geologic spans. Put it together and the map isn't a fog. It's lumpy. Slow, disk-borne direct collapse rogues haunt the plane and linger. Kick-borne and cluster-ejected rogues streak through on fast, rare visits. Streams add preferred lanes. For us, that shapes search strategy. We lean harder into the plane for long warning targets and keep a wide, fast watch for streakers at high galactic latitudes. Origins don't just tell stories. They point telescopes. We live inside a city of silent gravity, where rare passers leave long shadows across our calendars. The danger isn't malice. It's that a quiet approach steals time we can't afford to lose. The upside is real. When we catch the first twitch, we turn fear into time and time into choices. If you want the live rogue tracker and the build guide we promised, subscribe and jump to the next episode. We wire a real-time sky alarm from public data and show you how to use it. Share this with the one friend who loves space but hates surprises. Join us, and let's hunt the invisible together.